Good morning, everybody, or good afternoon to sixth period. This is Mr. Steele. Once again, I am not here in class. Today I'm over at Laguna Creek High School helping with their first ever challenge day. So unfortunately that means that I can't be with you. But of course, in this age of technology and robots, and sorry, that's the Star Wars universe, my bad. In this age of technology, I can find a way to still invade your potential day off and find a way to get you a little bit of calculus. So today, I'm going to be talking with you about a very small topic. Not a minor topic, but a small topic, something that's not going to require a ton of really deep analysis, but that still will show up and that you will be encountering as you work through differential equations in particular. And the topic in question here is actually called slope fields. Now in the past, and I assume you're writing stuff down at this moment as we speak, just as I probably should be considering I forgot to write the letters EQ for essential question. So if you're thinking about this, normally I used to be able to introduce this lesson just by pointing out that, in the textbook there are tons of slope fields, and every single chapter of assignments features at least one question about a slope field, even though you don't know anything about slope fields and they don't actually instruct you about slope fields. But as you guys are aware, I've kind of gotten rid of the whole textbook part. So instead, all I can say is slope fields are a thing, and they're a thing that you're going to encounter probably one time exactly on the AP test. But more importantly, they're a really nice tool to allow us to visualize differential equations, and more importantly, allow ourselves to visualize the solution to a differential equation, as you'll see in just a second. So in a moment, hopefully I'm buying you enough time to copy stuff down. In a moment, I'm going to show you a slope field, and then I'll start giving you a little bit of information, and then we'll work through constructing a slope field, which is the most likely task that you'll have to do. And then finally, we'll talk about how you can kind of reason your way through a slope field, or maybe even generate a potential differential equation that could be represented by a slope field. And then we'll be done. It'll move pretty quickly. I realize it's a Wednesday, and I also realize that you guys would probably benefit from having a little bit of time to work in class. And more importantly, I spent over 20 hours working on Cuddles Awakens this weekend, so I'm kind of running against the clock at this point, as you can kind of see down there in the bottom right-hand corner. So anyway, let's begin our discussion here. We're going to talk about slope fields and about this tool that we're going to introduce. So first of all, if I want to begin this lesson, I'd point out that a slope field is a tool. I don't know if people still use that as an insult. That might sound kind of funny. Maybe you're laughing. No, I can't tell if you're laughing. So a slope field is a tool, and it's a tool of visualization. So it's going to be a tool that helps us visualize and what it visualizes is a family of solutions. So the way I'll describe that is as a tool to visualize a family of antiderivatives. But of course we know that antiderivatives are really just solutions to a differential equation. Sometimes it's a pretty simple differential equation. But in a sense, what we're doing is we're trying to visualize a family of antiderivatives. Another way to think about it is we're trying to visualize all possible general solutions to a differential equation. Might even be the fancier way of saying it, but it's too late. I already wrote it down. I really don't want to restart. So first of all, what a slope field looks like is this. I'm going to make it a lot larger than I probably should. There we go. There's a slope field. It's stolen directly off a TI-89. And as you look at that, it's kind of strange right when you begin, because it's not even clear what you're looking at. It looks like someone broke a bunch of graphs off. Maybe they're little pieces of pretzels, those little pretzel sticks, and they've kind of laid them out, and we're supposed to just assume that there's some rhyme or reason to how they're doing it. Well, in reality, I can tell you what a slope field is, and I'm going to, because that's kind of my job. So when we're talking about a slope field, and hopefully this writing is clear. It's really awkward to write in this longer 1920 by 1080 screen size, but whatever. A slope field includes a bunch of short little line segments. And in fact, that's the best way to describe them, is as short line segments. Sometimes I call them tangent segments. For the moment, we'll go with line segments. So it includes short line segments, and those line segments basically represent tangent lines. So we'll say that those guys represent they represent tangent lines to the graphs of general solutions, or to particular solutions. Sorry, it's really difficult to write, think, talk, and just plain old not have everyone around when you're doing it. Yeah, if I start humming Star Wars theme, like, you can probably figure out why. Okay, so what we're saying is slope field includes short line segments that represent tangent lines to the graphs of particular solutions. So each of these guys over here is basically a short chunk of a tangent line. So like there's a potential tangent line. Maybe it was to the curve that looked like that. I didn't actually hit that, but remember there's a trick. You just draw a really big point of tangency. Basically, we're trying to visualize pieces of those guys. Now, looking over there, what happens then, if you think about it, is when you draw a tangent line to a graph, let's say we're looking at a curve like this. If we draw a bunch of little tangent lines to the graph, what happens is they sort of, as we hopefully talked about a little bit yesterday, if you kind of attach them together, they sort of form something that looks a little bit like a graph, right? I mean, hopefully that's not too big a craziness. I mean, if we talked about linear approximation yesterday, you'd know that a little bit anyway. Tangent lines are pretty good approximations of the graph. What that means for us is that if we look at a set of those tiny little short line segments, we'll actually be able to visualize what the graph is that solves that differential equation. So watch over here. Hopefully you can see my little pencil cursor thing. That's kind of a new trick. So what I'm going to do is I'm just going to kind of follow. And I realize you guys don't have this guy to draw down, but just watch me draw. So right there, you can kind of see I followed a bunch of tangent segments. I don't know if this is a good visualization or not, but there are a bunch of little tangent segments. And in drawing those little tangent segments, it looks to me like I've drawn a shape that looks like this. What graph can you think of, or what graphs? Let's go with parametric graphs. What are two graphs that you can think of that have shapes like that? Anybody? Okay, fine, Davis, you can think of one. Okay, yeah, basically, assuming that you actually said something and didn't just stare at the screen, because that would be awkward. In reality, what we're looking at is a graph that looks like a sine or a cosine. It's something sinusoidal. It's kind of periodic. It's bouncing up and down. In fact, this is the slope field. Just let's write this all out. So what you're looking at right there on the right side of your screen, this is the slope field for a particular differential equation. It's for dy dx equals cosine of x. And now, of course, if you think about it for a second, we're talking about the slope field for dy dx equals cosine. That means we're talking about a function whose derivative is cosine. And what function has derivative cosine? That would be y equals sine. So in a sense, what we're looking up there at is a graph of a bunch of tangent line segments that have slopes coming from cosine. Like the slope is cosine of x. It's cosine of whatever the x coordinate is right there. And of course we know the solution, like the function whose derivative is cosine, is sine of x plus c, give or take a vertical shift. And in fact, that's what you're seeing over here, is if I were to take that shape and paste it in, and of course my computer didn't cooperate, I could draw another one right there. I could draw another one, oops, I'm having trouble here, if you can't already tell. So I could draw another one down here. Basically what we've got is a graph of a whole bunch of different sine curves. Like they're all vertical shifts of one another. And of course the reason is those are all the functions whose derivative are cosine. So in a sense, this is just a way to visualize a bunch of derivatives, like a bunch of different particular solutions that could potentially show up for a differential equation. Now, of course, that's all really complicated. There's a lot of like craziness that happens inside one of these little guys. But what I want to do instead is I want to focus on a couple little skills with a differential equation. I don't want you to try to do anything fancy here. I'm not even here, so it's a little bit difficult. But basically, here's what our plan is going to be. Our plan is going to be to start with just constructing a slope field. We just want you to be able to make one. Can you make me a slope field? Or make one for the, greater good, I don't know. So what we're going to do is we are going to construct a slope field. And of course, I got to tell you where you're going to start. Like, what is it I'm going to give you in order to construct a slope field? So we're going to do it from a differential equation. And kind of the cool thing here is that although we can solve differential equations using separation of variables, in a sense, these slope fields we'll be able to kind of sketch out and draw, regardless of whether they're separable or not. So in other words, we might not be able to solve a differential equation, but we can sketch out a slope field and get an idea or a sense for what kind of solutions we might actually run into. It's kind of a cool thing. So what we're going to do is actually a really simple task. It doesn't seem like it would be because it's a pretty complicated idea, but it actually is pretty simple. There are two things we're going to do. I'm going to use lots of pretty colors, sorry Jose, in order to show you what this looks like on the next page. So the first thing we are going to do is I'm going to ask you to calculate slope at some points. Actually, I'm just going to go technical here. I'm going to say at a bunch of points. So I'm going to go ahead and ask you to just, figure out what the slope is at a number of points. And of course, I'll tell you which points they are because it'd be kind of complicated if you didn't. Second, after we calculate those slopes, we're going to sketch little tangent lines. Like, you little mini tangent lines. Look at the little tangent line. Isn't it precious? We're going to sketch the segment. And of course, these are just segments of tangent lines. We're going to sketch the segments. Sorry, we'll just say segment. We'll go singular. Sketch segment with that slope at each point. So basically, I'm going to give you a bunch of dots. Those dots are going to correspond to ordered pairs, like say 1, 1, 2, 3, 0, 0, whatever the case may be. And then I'm going to ask you to use the differential equation to figure out what the slope would be at that point based on the differential equation, because of course a dE gives you the slope. It's just a formula to find slope given x and y. Once you've got those, then you'll just draw a little segment. So for instance, let's say you're doing some work and you get that the slope is equal to 0. Well, of course, if the slope is 0, that's a horizontal line. There's a horizontal line segment. That's a pretty good line segment. You're right. You guys I can't even get your commendations because I'm at Laguna Creek right now, or I will be. Anyway, let's say you have m equals -2. Well, -2 is a little bit steeper. It's negative, so we might draw something like that. Maybe we get something like m equals 1/51st. I have no idea why that would be. It'd have to be almost horizontal, maybe just like that, something really steady. And basically what you'll realize pretty quickly is the only thing that really matters are, do you know where the horizontal segments are, and do you have positive or negative slope correct? That's really all you end up being able to take care of here. It's really hard to do it. So in other words, this is usually graded pretty easily. It's usually an easy couple of points on the AP test when it pops up, which it did last year, so for what it's worth. Okay, with that in mind, let's go ahead and get ready and let's construct our first slope field. Yeah, I'm excited. Okay, so we're going to go ahead and start constructing our first slope field. And now, of course, just as a heads up, I'm not going to do a whole lot of examples here. I'm going to kind of let you guys see the examples and then let you guys play with it yourself. You'll see when you get your homework assignment or the problem set for the day. It's a pretty straightforward homework. It's a pretty straightforward problem set. So it won't take too long, and you'll get the hang of it pretty quickly. But if not, you can always just tune back into the video and watch this one again. I picked a pretty representative one here. So what we are going to do right here and right now, we're going to construct a slope field. And of course, this thing, let's try that. Ha! There we go. Tricked Windows Journal. Okay, so here's what we're going to do. We're going to sketch a slope field for this guy. It's a differential equation. That differential equation is dy dx equals x times y plus 1. And we're going to work our way through it. Now, something to kind of pay attention to as you're writing it down is just kind of looking at it. You can kind of realize that, wait, we actually have the ability to solve this guy. In fact, I'm tempted to say that I could probably solve it pretty quickly almost in my head. I'm thinking we'd end up with some sort of ln thing. We'd have c e to the x. It'd probably be c e to the x all minus 1. In fact, I think I just solved it in my head, in which case I'm awesome. So, with that said, what we're going to do is we're going to just try to sketch a slope field. If you want to solve it later and try to see if I did it correctly, or if you're watching this video from outside my class and you want to see if I'm an idiot that tries to do things in his head when he doesn't need to, feel free to do that on your own time. For now, I want to show you how to actually compute the slope field, sketch a slope field for the differential equation provided here. So looking over at our graph, it looks like they've provided us with exactly 9 points. Looks like -1, 1, 0, 1, and 1, 1. We've got -1, 0, 0, 0, aka the origin, and 1, 0. As well as -1, -1, 0, -1, and 1, -1. So we have 9 points. So that means that they want us to construct 9 tangent line segments in order to construct the slope field here. And of course, one of the more important things to do is to make sure you actually produce 9 of them. You don't want to miss out on one because that'd be an easy way to lose points on the question. So here's what we're going to do. I'm going to just pick one of those points. Here, why don't you pick one of those points? Oh, you chose the one in the upper left-hand corner, which is conveniently the one I was going to choose. Wow, isn't it amazing? We're basically psychic. Or or you're psychic, I'm psychic, someone's psychic, whatever. So we're going to start with that point. And you're going to see in a second that this is not that difficult. So what we're going to do is we want to figure out what's the slope at that point. As in, if there was a particular solution that went through that point, what would be the slope of the tangent line at that spot? And if you go, slope, how can I find that? I don't even know the particular solution. You don't need to, because it's literally, once again, hey, look, it's slope. That's just a formula for the slope. If we know the x and the y coordinates, we can just go ahead and find the slope. So for this particular point, -1, 1, upper left-hand corner, what I see is that x is -1, y is 1, so we get -1 times 1 plus 1 is going to be -2. And what that means is over there on that point, I've got to draw a small little tangent segment, not a huge tangent line, that's not good. Just a short little tangent segment that has slope -2. So again, what I'm kind of thinking is about 45 degrees, kind of gives me -1, so I'm going to make it a little bit taller. I'm going to go something like that. And in fact, I'm not happy with its location, I'm going to move it over slightly, make it look like it did that originally. There'll be no video evidence that I moved it. So, moving forward, we found one point. Let's find another one. And hopefully you're not still grumbling about the fact that I didn't print out little pieces of paper for you with 9 dots and a Cartesian plane on it. Hopefully you're able to kind of problem solve just a little bit here and very quickly draw out the shape without much fanfare, because I just did too. And it's green. Okay, so our second point. Let's pick one that's just kind of hanging around. Let's go with 0, 1. So looking up there, we want slope. I'm seeing that x is 0, y is 1. That's going to give me 0 times 2 is 0. Now, of course, that's kind of nice. Like 0 isn't like a disappointment. It's not like, oh man, I have no money. It's like, yay, 0. That's an easy one to draw. We just need to draw a horizontal line. And there is such a horizontal line. Hey, look, a dragon. Look how perfectly horizontal that line segment is there. Like, man, that's an awesome line segment right there. Clearly horizontal. Those are important. Something that's kind of interesting on the AP test is when they give you a slope field in order to graph, they really only grade you on the horizontal segments. It basically goes 1 point for all the horizontal segments being horizontal, and then 1 point for all the other ones not looking completely horrible. I'm not even exaggerating. That's basically it. So, okay, we found that one. Let's go try another one. This is so much fun. Let's look at 1, 1. M is going to be, that's a horrible one. 1 times 1 plus 1 is going to be positive 2. So I'm going to attempt to draw another fairly steep line segment. And there it is. I've drawn it. So now from here, it gets particularly boring at about this point. But at the same time, what else are you going to do? So while you guys are doing it, I'm going to keep doing it right off to the side. Could tell a story while I did it, except for the fact that that actually might be more difficult than I think. So I'm just kind of working my way through here. Let's see, it's going to give me -1 over here. It's going to be -1 slope, so I'll try to make it exactly 45 degrees. Now, before I continue and do like the 5th, 6th, 7th, 8th, and 9th segments here, something just kind of dawned on me. Basically, looking up there, I see a couple interesting things happening. So, in particular, the first one is I see that if I put in a point, and again, this is just me observing. You can totally go through and just compute all 9 points this way. There's nothing wrong with it. It's a really colorful way to live your life. Be happy. Now, from here, what I'm thinking is that if the x-coordinate is 0, just a thought. I'm just spitballing here. If the x-coordinate is 0, then that means we'll have 0 times some number plus 1, and that's going to give us a 0. Now, the reason I bring this up is that it got really boring after doing 4 of them, and I really wasn't excited about doing any more. But I can start to take advantage of what I'd call like some sort of slope field symmetries by looking for ways and places that will always be 0. That way I can make sure I get the horizontal line segments just right before I even start to worry about it. So looking up at our picture, what other points we have, or what other points do we have that are going to have x-coordinate 0? Well, I see the origin will be one such point, and I also see 0, -1. So what that means is I'm just going to go ahead and slap those guys in. That's actually a really horizontal line. One's not quite as horizontal as the previous one, but I'll go ahead and make it look that way. So voila, there are 2 horizontal line segments that we already were able to take care of. Of course, it doesn't want me to fix it. So those 2 are taken care of. Now I also see something else that's kind of interesting. Like maybe you've thought of this, maybe you haven't. Use Adrian's brown here. The second thing is that although we figured out when x equals 0, if we plug in a different thing, if we plug in any number for x and y equals -1, our slope is going to be some number times -1 plus 1, which is equal to 0 as well. Which means that anywhere where y equals -1, our slope is going to be flat as well. It's going to be horizontal. So that gives us two possible points. That's going to give us -1 comma -1, and it's also going to give us 1 comma -1. Now technically there's a third point. This one also counted, but we already took care of that with x equaling 0. So in a sense we double found it. So I'm going to draw my horizontal line segments. That was not the most beautiful line segment in the world. Now it is. And then second, we'll draw one right over here. Hopefully you're noticing my horizontal line segments are pretty darn good from home. So there we go. We found those guys. At this point, you might go, okay, we're done. But unfortunately, we're not. Looking up there, are there any points that we missed? Yeah, as it turns out, there's one point left for us to actually deal with. That's going to be the point 1 comma 0. So without much further ado, I'm just going to go ahead and plug into it. I'm going to figure out that the slope right there is +1. In fact, something like that should be pretty appropriate. So at first, all we were doing was plugging in x and y coordinates into the differential equation because the differential equation spits out slope, and we wanted to know what the slope would be if there was a particular solution going through that point. Once we had that, though, it got boring pretty quickly. So, of course, instead, we started to look for ways to take advantage and basically figured out what makes the differential equation equal 0. Because once we had that, we were able to take care of a bunch of points all at once and produce this lovely slope field that you're looking at right here. Now, I happened to find on the computer while we were looking around, while I was looking around before the lesson, that there's actually a slope field generator on Desmos, so it's kind of cool. Let's go look and see if it looks reasonable. Let's just see. I mean, again, we're only zoomed in on a few points. I can see if I can zoom in there too. So here's the slope field generator. Our differential equation was x times the quantity y plus 1. So now there it is. Now, of course, we're looking to see, does this look about right? So let's see. So I'm just going to go ahead and snip it, kind of steal it my way in here and see if this looks pretty reasonable. Question is, does this look like what we found? Again, I don't know where this came from, otherwise I'd be giving credit for it right now. It's pretty awesome. So the question is, did we find a reasonable approximation of the slope field? Heck yes, we did. That looks pretty darn good. I'm pretty happy. Pat yourself on the back. Ow, not too hard though. Not too hard. Kind of sore. Okay, so there it is. We've just constructed our first slope field. Questions? Did I get you? But there it is. One constructed slope field, and it matches what Desmos has, which is kind of nice. I like matching Desmos. Desmos is cool. Alrighty. Okay, with that in mind, I do have a few more little things for you to do, but of course it's been a little bit of time, so what I'd rather do is I'd rather hype you up even more for Cuddles Awakens, coming this Friday to a classroom near you. So I'm going to go ahead and play the commercial again from last time, even though I will point out some of the footage has been improved significantly, and there is a little bit more animation, and if you like seeing BB-8 do funny, cute things, you're going to be in luck because there's a few of those in there too. So without further ado, the commercial, the trailer, the official trailer, not the teaser trailer, but the official trailer for Cuddles Awakens, coming this Friday. Okay, welcome back. So just to kind of point out, the trailer didn't have improved animation. The actual movie does, so you're in luck. There's going to be some pretty cool stuff there. Also, if you like portals, there will be a few portals in order to tie things together. But anyway, that's beside the point. Our job today, slope fields. What we've done so far is we talked about what a slope field was. We looked at kind of how they were helpful. Then we moved on. We actually constructed a slope field, first mind-numbingly, and then later by taking advantage of some sort of slope field symmetry, which was just basically looking for where by looking for where the tangent lines would be horizontal. At what points would we have horizontal slope or zero slope? And now at this point, basically the only thing left is to kind of ask you to look at a slope field and try to figure out what might have been the solution to it. So on the next page, what I have plotted for you is a slope field. Now, I can't actually tell how readable your slope field is, but even if you can't read it, it doesn't really matter because it's really the words that I'm going to be saying. It's going to be the words coming out of my mouth right here that are really more important. Now, there is a difficulty because, of course, you can't see my mouth moving, nor are the words actually coming from my mouth at the moment that you're hearing them. But setting all that stuff aside, basically what I want to show you is the way to kind of reason your way through a slope field. Now, there are a couple different possibilities here. Like if someone asked you to come up with a potential differential equation that's represented by a slope field, or even what is a potential solution to the slope field, it's usually about just recognizing the shape. Like trying to look at the graph and going, yeah, I don't know, maybe. Like just kind of like thinking your way through it. Unfortunately, it's not going to be the case every single time, as would be demonstrated right here. Like as I'm looking at it, and again, you don't need to graph it down. I think just listening will be plenty. As I look at this guy, I see some stuff. It sort of looks sort of parabolic, like kind of see something like that happening. But then again, I'm not 100% sure. And here it looks kind of shaky, so I don't really know. So in this case, what I'd rather do is I'd rather just kind of focus on stuff that I can kind of control. Like what is there that I see up there? What is informative about this slope field? And I'm going to give you a hint. It's not any of these little slanted segments. Nobody cares about those slanted segments. What everything in the slope field world is all about is horizontality. That's not a word. Everything in the slope field world is about being horizontal. People love horizontal. Like they were just super into the whole planking thing in slope field world. And of course the reason why is when something's equal to 0, it tells you that the slope field's equal to 0 as well. Because the slope field is just code for figuring out what the slope is. So what I'm going to do is I'm going to look at this picture, and whether you can see it perfectly or not, it's not going to really change anything. I'm going to look at this picture and I'm going to attempt to identify the places where the slope is horizontal. Like where are the tangent segments that are literally horizontal? So I see a couple different options, but I see one in particular first. Looking right here, I see a whole row, a whole horizontal row where the slope is horizontal. You can't see my arm, but my arm's horizontal also. So if someone in the front row could just like put their arm up at a horizontal level for a second. Cool, thank you. That's what I'm talking about right here. It's horizontal. So now we got to think about, well, what does that tell us? Well, looking up here, we want to figure out a potential differential equation. And again, you can kind of figure out. On the AP test, this will be a multiple choice question. You just kind of reason your way through it. So I'm kind of preparing you for that kind of idea. So looking up there, we have horizontal line segments, a whole bunch of them. Now I might ask you, where are those horizontal line segments happening? Because again, what we're doing is we're just kind of like mining it. We've got horizontal segments. And the question is, well, where are they happening? Because that where is going to give us a bunch of information. So you tell me, where is it that they're happening? Come on, tell me something. Anybody? Come on, someone can answer the question. You can't see it, but I'm very frustratedly putting my... Oh, yeah, there's no one here. I'm talking to a wall. My bad. Okay, so where are they horizontal? That one looks like it's happening at y equals -2. What tells me that? Well, the fact that it says -2, it's below the x-axis. It's just a pretty reasonable guess. So that tells me we've got horizontal segments at y equals -2. Where else do you see some horizontal segments? And depending on your vision, you may or may not be able to see it. So I'm looking for you on your behalf. I also see horizontal line segments right there. Looks like there are a whole bunch right in that spot as well. So right there, where is that happening? Well, the graph's kind of ugly looking. I'm just going to assume that it's happening right there. I also see them happening at x equals 3. So cool. There are horizontal line segments also at x equals 3. The question, of course, becomes, what does that tell us? Like, how does that fix our problem? We're supposed to come up with a potential differential equation for this very slope field. What does that tell us? Well, we know that horizontal segments happen when the slope is 0. In other words, these are the places where dy dx equals 0. So looking over there, if the differential equation has to be 0 at y equals negative 2, that should tell us that there must be a factor of y plus 2 in the differential equation. Like the rate of change has to be proportional to y plus 2. That way when we plug in y equals negative 2, it ends up being equal to 0. That tells me that right up here in our differential equation, we need a y plus 2. Second, definitely important as well, if that happens at x equals 3, there also needs to be a factor of x minus 3. Because otherwise, how would we plug in x equals 3 and end up with 0? We couldn't. So basically, that's our second piece. We also need to have x minus 3 in there. And in fact, what we just did was we just found a potential differential equation. Now, is this guaranteed to be the correct one? Absolutely not. We could have any number. Basically, it's just got to be proportional to those two. There could be a k in there. Not that there has to be, but there could be. So just know that that's a potential one. Now, how reasonable was this? Let's go ask Desmos to kind of spot check for us. Like, does this look like a reasonable facsimile of what we just looked at? So we got y plus 2 and x minus 3. Y plus 2, x minus 3. Y plus 2, x minus 3. What is that? Why stop? Y plus 2, x minus 3. Okay, so of course we're zoomed in here. Let's go back to standard. Okay, now according to our little picture here, it shows us, let's see, this isn't maybe going to be perfect, but let's see what happens here. So according to the Desmos slope field generator, wonderful tool, our slope field should look a little bit like this. Does that look pretty good? And I'm not going to be able to match it up exactly, but notice you got horizontal ones. I'm going in a vertical line right about there. There they match. And then I see horizontal ones on a line down there. Everything looks pretty darn good. It's a little boxier on the Desmos one, and it's way more colorful. It's much more likely to be red, although I don't know who greenlit those orange segments. But basically, yeah, it looks pretty darn good. I'm going to go ahead and say that we figured that one out. So as kind of a key, if you're looking to determine like what would be a potential slope field here for what I'm looking at, the reality is your job should be figuring out where does the thing have horizontal segments, because those correspond to the zeros of the differential equation. And of course, there are a lot more ways to figure it out. There are a lot of potential answers. Like this is just one way, but I tend to find this is a pretty successful way to navigate it if you don't just automatically recognize a parent graph. You know what I'm saying? So for instance, like if I had graphed up here 1 over x, you're supposed to just look and go, oh look, it looks a little bit like an ln. Or if I graph 2x, you're supposed to go, oh, that's sort of quadratic. So I mean, if you recognize it, great. But if you don't, look for the horizontal segments. Those horizontal segments will be your guide. It'll take care of everything for you. Pretty cool, pretty slick. Okay, so with that in mind, we basically hit everything that's possibly out there. The last thing I want to do is just kind of throw at you a few words, like just kind of leave you with some parting thoughts here about slope fields. So here they are. If you're asked to match a differential equation to a slope field, really you can just focus on the horizontal line segments, like the segments that have slope 0. And of course we just saw why, because those slopes tend to cue us into the zeros of the differential equation. They allow us to match things up. Now what I've graphed next to you, or what I've used the Desmos slope field generator, beautiful invention, thank you to whoever made it. What I've used that for is I've put up there a slope field that's non-separable. And basically it's kind of strange, in fact. And if you're looking at that, it is pretty confusing. Like if I asked you to actually go through and figure out what dy dx is, you might be up a creek without a paddle. Like it'd be pretty rough. But if we go back to our strategy from before, you can have a pretty strong idea about what's actually happening here. It's really, really neat. So my question to you, just in looking at it, as you're sitting in your desk looking at it, probably squinting at it if we're being honest, as you're squinting on it, the question is, where are the horizontal segments? And the answer to that question would be, they're all right here in the middle. That's horrible. That was just awful. They're all right here. It's all those guys. Basically, all those horizontal line segments are right there, 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 there. In fact, I can just circle them individually so they're a little bit cleaner. There, 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 all of those guys. So looking at them, the question is, of course, well, you know, what is that telling us? Like, what are they showing us? Where are those points? Well, again, this is just kind of well, it's not a guess because I know what the answer is. I created the equation. But looking at it, as complicated as this is, we can actually kind of see that each of those horizontal segments is centered at a point. And each of those points, 0, 0, 1, 1, 2, 2, 3, 3, 4, 4. Something you might notice is that every single one, the x and y coordinates are the same. The reason why is the fact that that actually is the solution to our differential equation. Basically, m equals 0 along the line y equals x. And what that means is if y equals x and we need the slope to equal 0, it must be proportional to, or it must be a multiple of, is another fancy way of saying it, some version of that equals 0. So basically what that implies is that y minus x has to equal 0. So in fact we get y minus x as our differential equation. Or possibly x minus y. It's proportional to it, we can't really tell. And in fact, all I did was, again, I looked for those horizontal segments. Those horizontal segments were my key. Now if I go over to Desmos and look at it, oh, it was x minus y. How would it be different if I did y minus x? Let's just kind of think for a second. It doesn't look any different. Basically the same, because of course it's proportional to that guy. So there you go. It looks pretty solid. You can use that with all sorts of other ones. This is an old favorite of mine. So this is a pretty complicated one, but if you're looking at it, notice that here, I'll snip it in just really quickly, just because it's kind of fun. Like, honestly, I am actually having fun. I'm kind of glad I did this. It's actually, whoa, what is that? What is that? Hello. No, I don't like that. I don't want to play with that. Okay, well, it doesn't want me to switch it. Okay, well, here it is. Here's our little segment here. I put in y minus x squared. So basically, let's see. Looking at this guy, we're looking for zeros wherever the parabola y equals x squared is. And notice that, again, we've got a bunch of different ones here, but it's kind of crazy. The horizontal segments match up right there. So basically, it's equal to 0 along those lines. Now, again, would I ask you to come up with that on your own? Heck no. But for the moment, it's just kind of cool to see. And with that, I think we're ready to call this, put this lesson in the books. So before we call it a day, are there any questions? Hopefully I didn't get you that time. So looking here, what have we done today? We defined what a slope field was. It's basically a way to look at an entire family of functions that could potentially solve a differential equation. The way we graph a slope field is by graphing really tiny tangent lines, like cute little tiny baby tangent lines right there. Look at the little baby bottle for the tangent line. And we graph those guys. And by looking at them, we're able to kind of get a general gist of the trend, or basically what one member of that possible thing would be. In other words, what it would be one particular solution that could solve this differential equation. When the task comes to actually sketching out a slope field, the more likely task that you're going to be handling on my test, the AP test, etc., basically what we do is we just figure out what is the slope at each of the points, and we'll predetermine the points for you. We'll give them to you so you don't have to worry about, did I pick the right ones? And voila, we were able to do that. We were able to take advantage of the fact that whenever something's equal to 0, like a certain coordinate could make the entire differential equation 0. So that allowed us to skip some steps and save a little bit of time, which we did there. Big hand to Desmos for helping us out. After that, we looked at some fairly complicated differential equations, and we tried to figure out ways to generate a potential differential equation for them, like just trying to go from that slope field backwards. And what that looked like for us was finding the horizontal segments and then trying to backwards engineer exactly what that differential equation might have looked like. And then finally, even with some weird ones, the key really came down to those horizontal segments. It's really one of two things. If you recognize a function with it, try to go with that. If not, where are the horizontal segments? And if you know where they are, you're in basically pretty darn good shape with everything that you're going to be asked to do. And without further ado, I'm going to pass this off. You guys can use the rest of the period to get a jump start on the homework assignment and kind of work your way through it and start to get really comfortable with slope fields. It's just another small tool in your arsenal. Tomorrow will be the last lesson, of course, for this unit. And basically what that means is Friday will be Cuddles Awakens. Okay, enough of that. Thank you guys for listening. Enjoy the rest of your day. Hopefully the lesson worked well. If not, we'll see you tomorrow. So have a good one, guys. And thank you to the substitute, whoever's covering my class. Thank you for that as well. Have a good one, everyone.